Okay, so hello everyone. I'm Gitanjali Jaina. I'm a research scholar from IIT Delhi, and I'm the PMR TA for this course, which is Physics of Linear and Non-Linear Optical Waveguide. So, as I used to say in all the live section, we will in each live section we'll go through the concept that has been taught in during this week, which is for now it is week 10. So whatever that has been discussed in week 10, based on that concept, I will solve few problems, numerical or conceptual, that is related to this weekly content. And based on that, we'll solve those problems. And besides that, if you have any doubts, I will also try to clarify that. Okay. So this is week 10. In the last week, we have solved up to question number 9. So, two of the questions still it remains. So, we have to solve that, which is based on the fiber Bragg rating. So, let us first solve those problems first. Then we'll move to what are the nonlinear effect of an electric field inside a medium, and how to find out the polarization and the electric displacement vector, and how does the tensor looks like. So we'll solve all those problems. So let us quickly see up to which part we have solved. So question number 9, so it has three parts. So we have already solved part A and part B. So to give a brief overview, uh, let us see what we have solved in part A and part B. So in part A, the question it's based on a planar waveguide. The refractive index of the core and the cladding it was already given, which is N1 is 1.51 and N2 is 1.50. And it is also given what is the core radius, which is 2 micrometer. So the question number 1, it asks about what are the total number of modes supported by such waveguide at lambda 0.6 micrometer. This was the first part. We have already seen that. So to find out what are the number of modes, as I said before, we first need to find out what is the V number of this planar waveguide, and based on that we have to divide it the V number by pi by 2, and we have to take an integer that is greater than and closer to the whatever value we are getting. So in the last session, we got a value around 1.156 for the ratio V by pi by 2. And based on that, we conclude that the planar waveguide, it will support two modes. Okay, so the first mode will be TE0 mode, which is the fundamental mode, and the second mode will be the TE1 mode. TE0 and TE1 mode. In the second part, what we have seen, so in the second part, it was already given what are the effective refractive indices of the TE0 and TE1. So TE0, it was given 1.50862, and TE1, it was, so for TE1, it was given is 1.5046. And the question asks about what should be the grating period of the fiber Bragg grating for effective coupling between these two modes. So we need to find out what is the period for this problem. So it's easy. So we just need to for effective coupling, what we need gamma should be 0, so that the kappa, it should be equal to beta 1 minus beta 2. So, or you can take it as a delta beta, which is beta 1 minus beta 2. Okay. So effective refractive indices are already given. That means we can easily calculate what are the values of delta beta, because delta beta is nothing but K0 delta n effective. K0 we already know, this is 2 pi over lambda 0, and n effective is n effective T0 minus n effective 1. So by using this, we can easily calculate what will be delta beta, and from that we can easily calculate what is the period of this planar waveguide. And we have already seen it in the last class that it will come around 149.3 micrometer, right? So for the next part that we haven't solved, the C part. So for C part, first we have to, what you have to do, we have to see how the power coupling between this T0 and T1 mode will occur inside a fiber Bragg grating. Because in the class we have already seen how the power coupling between a forward propagating mode and a backward propagating mode can happen. But for this part, these modes are co-directional. It's like they are moving in the same direction. So that is why the expression for the exchange power or the power coupling, the expression should be different here. Okay. So for that, so let me give a let me write the expression for co-directional coupling. So in overall, what we have uh, to excite the power. So the power coupling, power carried by the propagating mode, if we are assuming that we are exciting first the T0 mode, and as the mode propagate inside the fiber Bragg grating, so some of the power get coupled to T1 mode, and based on that we'll see what are the expression for the power coupling, the expression for power coupled to T0 mode or T1 mode. So power carried by propagating mode, if we excite T0 mode at the input. So before that, we can see the schematic of the power coupling. So it's like if you take, let us say, so this is the transverse cross section of the fiber Bragg grating. So first we are exciting, let us say we are exciting the T0 mode first. So the profile will be, so what will happen after some distance? This field profile will change. So gradually what will happen, the T1 mode, it will come into the picture. And after some distance, we'll see that most the input power will be coupled to the T0 mode. So we have started with T0 mode. Then we end up with T1. So this is a different, this is the direction of propagation, and this is the field profile. So the expression will be more and less similar to what we have seen in the directional coupler. So for this one, so if you use the, so I'm not going into the details of the couple mode theory. It is already explicitly explained by the professor in the lecture. So please go through the lecture. So I will just write down the expression for the co-directional coupling. So when we have such condition, so let us say we are having now pure phase matching condition. So for pure phase matching condition, the gamma, it should be 0, right? Gamma should be 0. So we'll consider two cases. First is pure phase matching condition for co-directional coupling, and other cases when we have when we don't have pure phase matching condition. So when we have gamma equal to 0, so you can see when we excite T0 mode, let us say the power coupled to T0 mode, it is P1, and the power coupled to T1 mode, it is P2. Okay, so we are exciting first T0 mode, and as the mode propagate, so it get the power get coupled to the T1 mode because the fiber support both the modes T0 and T1 mode. So for P1, the expression will be coefficient of AZ square. So this will come as cos square kappa z. And for T1 mode, this is P2. This will be square of BZ square, and this is sine square kappa z. Okay. So this expression more and less this is similar to what we have seen in the directional coupler. So we don't have to remember that much. If you can take the analogy, then you can easily identify what are the expression for P1 and P2. And similar to the directional coupler. So for so if you see for a distance z pi by 2 kappa, at this distance we have P1 z pi by 2k, it is 0, and P2 when z is pi by 2k is 1. So let us say the power coupled is P1 is 1. So that means most of the input power is coupling to the after this much distance, the input power will be coupled to T1 mode. So that means we have now the coupling length for this co-directional coupling. This will be pi by 2k, 2 kappa. This is for pure phase matching condition. So when we have, let us say we have other case where the gamma, which is, if you recall the expression, this is beta 1 minus beta 2 minus kappa, when this is not equal to 0. So for this case, instead of kappa, now we have gamma. So P1z, it will be square of AZ square. So this will come as cos square comma z. So I'm just writing down the final expression because going through the couple mode theory again, it will be not good for this live section. So we can go through the lecture to find out the intermediate steps. Okay. In P2Z, it is square of BZ square. So this will be 1 minute. Could you please start from the beginning? Okay, beginning of this question. Okay, let me go again then. If you remember, we have already solved we have solved up to question number 9, and in first two part we have seen what is the number of modes supported by the fiber planar waveguide. So these are already given in the question. N1, N2 is given. A is also given. Lambda 0 is also given. So based on that, we have calculated what is the V number so that we can get what are the total number of modes supported by this planar waveguide. So this you can easily remember. So we have seen how we can, what is the trick to find out the total number of modes in a planar waveguide. So it's not for the fiber. So make sure you are using the correct trick. So this is for the planar waveguide. Okay. For fiber, it was different. So if you remember, it was something between, if it lies between m plus 1 pi by 2 to m pi, then it will be this number of modes. So please go through that trick again. So this trick is for the planar waveguide. This part is done in the last session. And next part, it was asking about what is the grating period for the fiber, so that the TE0 mode and TE1 mode, there will be efficient coupling between TE0 and TE1. So because N effective was given, and the period, which is nothing but 2 pi over delta bit, right? So delta beta we can easily write it down as a K0 delta N effective, and delta N effective we calculate. So it is already given in the question. Okay. Or if not, if you have access to your laptop, then you can easily calculate what are the transcendental equation for T0 mode and T1 mode, and based on that you can calculate what is the N effective. So based on the intersection point that I'm talking about. So based on that, we can easily calculate what is the period, right? So this part we have seen in the last session. So the part that we haven't covered is the last part is the question was it was asking about, assume that kappa is nothing but the coupling coefficient. So it is given as 0.421 centimeter inverse. Then calculate the length at which the complete transfer of power will take place. So it was asking about at which distance we'll see that most of the power, not most of the power, all the power will be coupled to TE1 mode if you excite the TE0 mode. Okay. So for efficient coupling, we know the period. So if you make the period in the fiber bracket, and then there will be a complete transfer of power. So this is the profile, how the mode get coupled from T0 to T1 mode when the mode it travels through the fiber bracket. So based on the exchange of power, we'll see that when we excite T0 mode, this is mode profile for T0 mode. So based on that, we'll see is the mode propagate in Z direction. We are seeing that the power is getting coupled to T1 mode. Okay. And this is co-directional coupling. So by co-directional, I mean the both of this mode T0 and T1 mode, they are propagating in the same direction, like in this direction. It's not like one mode is propagating in this direction and one mode is propagating in this direction. So this is contradirectional coupling. So if you remember, we have already solved that. And this is co-directional coupling. Okay. So for this case, contradirection for the power expression for contradirectional coupling, it's different from co-directional coupling. So that is why I have written down what are the expression for power coupling, so that if you know the powers, the expression for power, then we can easily find out what is the distance at which the coupling will take place. Okay. So this I have already explained. So P1Z, this we'll get from couple mode theory, that P1Z will come out as cos square kappa Z when we have gamma is 0, that is pure phase matching condition. And P2Z, it will come out as sin square kappa Z. Okay. So from this expression, we can see that P1 is varying as a cos function and P2 is varying as a sine function. So, and from here we can easily put P Z equal to pi by 2k. We'll see that at this distance, the power P1 it will be 0 and power P2 it will be 1. Okay. So that means this is the coupling distance. So in the next part, so only this much is required for our given question. Okay. But this is only for information. That is for the sake of completeness, I am writing it down. So when we have gamma not equal to 0, so in that case, what we have, the power expression, you can write it as az square. Okay, I have already written down here. So this is cos square kz plus gamma square by 4. Okay, so this is for T0 mode. For T1 mode, we have kappa square over gamma square sine square gamma z. Okay, so gamma here, gamma square, it is nothing but kappa square plus gamma square by 4. So this you can use it when gamma is not equal to 0. So let us see what we have for a given question. In the question, the kappa, so it is already given 0.421. So length at which complete transfer of power will take place. So for complete transfer means gamma, it should be 0. So that means we can use this expression. So Z will be pi by 2 kappa, which will be pi by 2, 0.421 centimeter inverse, and this will come out as 3.73 centimeter inverse. So is this problem clear to you? So this is all about question number 9. Okay. And remember that this is for co-directional coupling. So don't get confused between co-directional and contradirectional coupling. So if this question is clear, so I will move to the next question. Do you have any doubt in question number 9? Okay. Okay. So let us move to question number 10 then. So question number 10, it's based on the chopped fiber Bragg rating. So why do we need chopped fiber Bragg rating? So we'll see that this fiber Bragg rating is needed to compensate the dispersion. So we've seen there are two types of dispersion. One is normal dispersion and anomalous dispersion. So based on the sign of the dispersion, different wavelength will travel at different speeds. So to compensate the speed, we need this chopped fiber Bragg grating. Okay. So now we'll see how it can compensate that. Okay. So this question is based on application. So a chopped fiber Bragg grating is written in an 25 long optical fiber which supports the fiber mode of an effective 1.45. So length of the total length of the fiber Bragg grating is given, which is 25 and it is also given that the supported mode has effective index 1.45. The grating period is linearly tapered along the grating length such that local grating period in nanometer is given by this expression. So now in this fiber Bragg grating, the period of the fiber is changing along the length of the fiber. This is gamma 0 minus alpha z in, so z is in nanometer. Sorry, it is in millimeter. Okay. Now the design is such that the input end at the input end z equal to 0, lambda b is 1552 nanometer. So that means for this fiber Bragg grating, we have different length. So as the z increases, we'll see the period decreases. So it is decreasing as we move along the fiber Bragg grating. Okay. So lambda b is given at z equal to 0. The Bragg wavelength is 1552 nanometer. And at the output end, that means that z equal to L. So the total length is L. So that means this is z equal to 0. This point is z equal to A. So like I say, the fiber Bragg grating is up to this. So z equal to L is 1542 nanometer. So in the first part, the question is asking about determine the initial grating period, which is lambda 0, and the chop rate. What is the chop rate and what is the initial grating period in nanometer per millimeter? So let us see this first. Then we'll move to move to the second part. So we now need to find out what is lambda 0 and what is alpha. This we can easily calculate it because these conditions are given to us, right? So it is given lambda b at z equal to 0 is 1552 nanometer. And we have the expression for, so we know that um, this is the Bragg condition, like ineffective. So lambda b z is, it should be this. So for the 0, it should be lambda b 0. When z equal to 0, this is an effective, gamma is 0. So gamma z is given. This is not gamma, it is inverted v alpha z. So when you put 0 here, we'll get this would be So that means we can find out what is initial grating period, which is lambda B0 over 2 n effective. So this is 1552 nanometer, 2 into 1.45, and this will come around 535.17 nanometer. So for the initial grating period, we have the value. For the chirp rate alpha, we can use the second condition. So what we have, lambda b at z equal to L is 1542 nanometer. So that means for this expression we have lambda L is lambda 0 minus alpha z. Z is nothing but L, which is 1542 nanometer. This we have already calculated it, and L is also given. It is 25 mm. So that means alpha, it would be initial grating period minus 1542 over length. So this is 535.17 minus 25. So this will come around 0.1378 over nanometer per millimeter. Okay. Now let us see the second part. The second part, find the position along the grating period at which the following wavelength is reflected. Lambda 1 is 1552 nanometer, lambda 2 is 1550, and let us say this is lambda 3, which is 1541 nanometer. So we need to find out the location at which this wavelength is getting reflected. So to find out the position, let us see. We have lambda 1, which is 1552, lambda 2, 1550, lambda 3 is 1541. So we can use the Bragg condition, that is lambda bz should be equal to 2 n effective gamma z. Right? So for the first one, let us see the first one, which is lambda 1. Okay, so we need to find out z, right? So let us see first what will be z. This is initial grating period minus alpha z. So that means z will come out as so z will be 1 by alpha initial grating period minus lambda b z to an effect. So this is the expression to find out the location of reflected spectrum. So lambda 1, lambda 2 is already given. Lambda 0, we have already calculated it also. This is 535.17 nanometer. Alpha, we already know. This is 0.1378 nanometer per millimeter. Also, we know the N effective, 1.45. So that means we can easily use the expression to find out the Z. So lambda B, it is one is 1552 nanometer, 1550 nanometer, and 1541 nanometer. So if you use this expression, you will see that this for this one, this will be reflected at the input end. This will be reflected after traveling 4.99 or 5 millimeter, and this will be reflected when we have 27.5 millimeter. So these are the location at which the this wavelength will be reflected. But if we recall, the total fiber length is 25 mm. So that means this wavelength, it will be easily propagate through this fiber without any reflection. So this won't suffer any reflection. So to see this schematically, what we have. So we have the fiber Bragg grating where the period is decreasing along the fiber. For this fiber, what we'll see that at the output end we'll have 1541 nanometer, and the 1552 nanometer, it is reflected at the input end. Next, uh, 1550 nanometer. So here we can easily see that the higher wavelength, when we have a grating like this, like if the period is decreasing along the length of the fiber, so we'll see that the higher wavelength, it will be reflected first, then the gradually the lower wavelength will be reflected. So this can be used to compensate the dispersion where we have a situation like consider a situation that the higher wavelength is moving faster than the lower wavelength. Okay, so for that case, what this type of chopped fiber grating, it will decrease the speed of the uh, higher wavelength. Okay, because it is getting reflected at the input end, right? So that means the speed will decrease now. So in this manner, we can compensate the dispersion in a fiber. Okay, so I think this problem is clear. If not, let me know at any time. You can feel free to stop me and ask your doubt. Okay, so let us move to question number 11, which is a conceptual one. Can you please go through the question and can you please let me know what are the possible option you can think of for this question? So let me read out the question first. The question says, which one of the following is not true for fiber Bragg rating? One is option number A, lambda B experience redshift when we stress the fiber. Option B, when we heat the fiber, lambda B experience blue shift. Option C, chopped fiber Bragg rating can be used to compensate dispersion in a fiber. And option D, under pure phase matching condition, the power exchange between the fiber mode is maximum. So which one of the following is not true? Okay, either A and B. Okay, your guess is correct. Like these options, we have already seen the chopped one, and this is also true. For this case, what we need to see how the Bragg condition is getting affected, because from that we can easily guess which one of the following is not correct. So let us see the first one. When we trace the fiber, so let us see. The Bragg condition is like lambda b should be equal to 2 an effective gritting period. So when we stretch the fiber, that means we are, so let us say we have a fiber like this, where the period is like this. Now we are stretching the fiber. Okay, so we are stretching the fiber. So that means now this period, whatever period was there, it will increase, right? So when we stretch the fiber, this value will increase. So that means lambda b now will increase. Okay. So lambda is increasing means we will experience a red shift. So longer wavelength means if the system is going towards longer wavelength, it is red shifting, and if it is moving towards lower wavelength, it is blue shift. Okay, so that means this option is correct. For so that means the answer will be option B. But let us see first for B part. So it is saying when we hit the fiber, the lambda b experience a blue shift. So that means the lambda b will decrease if we hit the fiber. But so according to this equation, according to the Bragg condition, so when we hit the fiber, this N effective will increase. So if you hit the fiber, the effective refractive index will increase. So that means the lambda v is, will also increase. So lambda is increasing means we will see a red shift, not a blue shift. So that means the answer will be option B. Okay. So let us move to question number 12 then. How can we see that an effective will increase with temperature? Because an effective is nothing but how the propagating mode, how the medium will resist the propagation of mode inside this fiber vibrating. So we can see we can take an analogy like this. So when we heat the water, so let us say we have a water container, we are heating the water. So that means the vibrational energy of the water molecule will increase, right? So it is similar to that case. It's like the vibrational energy will increase. So when we heat a fiber, that means the molecule. So fiber is made up of some material, right? SiO2, silicon. So because of heating, so there will be vibration in the fiber, in the molecules inside the fiber, and because of that, the modes will experience resistance to propagate inside the fiber. So that means N effective is increasing. Okay. So N effective is high means there is more resistance. N effective is low means there is low resistance. So it is like that only. So if you cool down, then it will be opposite. Okay. So let us see question number 12. So please go through the question once. Okay, let me read out first. So question 12 says a fiber Bragg grating. So this will be, I think, one more problem is there. for fiber bracketting. Then we'll see what are the nonlinear effect of fiber. So a fiber Bragg rating is single mode fiber. SMF means single mode fiber with effective index of the core mode is 1.455. So ineffective it is given 1.455. So say resonance at wavelength 1.5 micrometer, that means lambda b is 1.5 micrometer. If the grating length is 1 mm. So total length it is given 1 mm. And the peak reflectivity is 98%. That means R is given, which is 0.98. Obtain the value of grating period and the coupling coefficient and the bandwidth of the reflected spectra. So you are given this much information. We need to find out what is the grating period, coupling coefficient, and the bandwidth. So if you know the formulation or the formulas, the different expression for this, you can easily find out the options for this question. Okay. So I think, please give me one. Okay, one is there. Can you calculate what will be the period if you have this much information? So please calculate whether you are getting the value of grating period or not. Point 515. Yes, you are correct. So I think we have calculated in terms of micrometer. Okay, grating period is correct. Zero, it will come around 0.515 micrometer. Okay, so you know how to calculate grating period now. Kappa, is it possible for you to calculate kappa now? How you can calculate kappa? Let me know whether you know the expression, you know the relation. If not, then I will give you a hint. Okay. So for kappa, what we do is, see, we know the reflectivity, right? So reflectivity, the expression for reflectivity is nothing but tan hyperbolic square kappa L. So R is given, so that means you can easily find out what is kappa now. You just need to take the inverse of tan hyperbolic function. Delta n is not given. Okay, so there are different ways that you can calculate kappa, right? Uh, like I think you are talking about the phase matching condition. 2 beta is kappa, so kappa will be K0 delta n effective. So that you can also follow, but here delta n is not given. But what we have given is the reflectivity. Peak reflectivity maximum is 98%. So that means you can take this expression for reflectivity. So 10 hyperbolic square kappa L. So kappa L you can easily calculate now, right? So just look for what are the information that is has been given to you. So this will be the simple expression. You can easily take the inverse of 10 hyperbolic, or you can take this is will be 1 by 2 in ln 1 plus tan hyperbolic kappa L 1 minus tan hyperbolic kappa L. So R is given, it is 0.98. So tan hyperbolic kappa L, it will come around 0.98995. L is also given, it is I think 1 mm. So we have 1 by 2 ln 1 plus 0.98995 1 minus 0.98995. So this will be 2.64 millimeter inwards. Yes. Okay, so you know how to calculate kappa now. So let us see what will be bandwidth. So let me give you the bandwidth expression. So bandwidth of the reflected spectrum. This I have already covered in the previous live session. So for third part, the bandwidth it is given by lambda b square n effective L square root 1 plus kappa L by pi square. Lambda b is given, it is I think 1550, no, 1500 nanometer. N effective is given 1.455. L is also given 1 mm. So lambda b is given. So be careful of the units. And effective is 1.455 and this is 1 mm. 1 plus kappa L will be, because L is 1 mm, so this will come around 2.64 by 3.14 square. So what is the value you are getting? This So we will get a value around 2 nanometer or 2.02 nanometer to be specific. I think we will get it. Should I move to next question or yeah, around this 2 nanometer. Okay. So let us see question number 13. Question number 13 says a fiber Bragg rating has a Bragg wavelength of 1550 nanometer at room temperature 25 degrees Celsius. And the thermo-optic coefficient, which is eta of the fiber, is given. So it is 6.5 into 10 to the minus 6 per degree Celsius, and the thermal expansion coefficient alpha is also given, which is 0.55 into 10 to the minus 6. So in the first part, it is asking what is the change in Bragg wavelength when the temperature increases by 15 degrees Celsius. And in the B part, the question asks what is the new Bragg wavelength after the temperature change. So lambda B, it is given 1550 nanometer, 825. Theta is given 6.5 into 10 to the minus 6 per degree Celsius. Thermal expansion coefficient alpha is 0.55 into minus 6 per degree Celsius. So what is the change in lambda B when we have a change in delta T? So if you recall, we have an expression delta lambda B by delta lambda is the sum of expansion coefficient, thermo-optic and thermal expansion coefficient multiplied by delta T. So all of the parameter is given alpha, eta, lambda B and delta T. So alpha is 0.55 plus eta is 6.5 into 10 to the minus 6 and delta T is 15 degrees Celsius and lambda B is 1550. So this will come around 0.45564. Okay, so we know the answer for delta lambda and finding the new Bragg wavelength is easy because lambda B is already given and we know delta lambda B. So that means the new Bragg wavelength lambda B prime, it is lambda B plus delta lambda B, which is 1550 plus 0.5464. Okay, so this is all about the fiber Bragg rating. So do you have any question? Otherwise, we'll move to the nonlinear effect. Okay, if not, then let me move to question number. So this is the we'll see the problems based on the nonlinear effect now. Okay, so the first question, it's based on, so question says a linear dielectric medium is subjected to different electric fields and the resulting polarization are measured. So we have a nonlinear dielectric medium. Now we are exposing this medium to a different electric field, not only to one electric field but different electric field, and we know what is the effect on the polarization. So these are already given. So these are three kinds of electric field that is being applied in the system in the linear dielectric medium, and these are the three response that we are getting. So using the given data, determine the linear susceptibility of the medium. So let us see. So if you recall, in a linear dielectric medium, we have, you can express the polarization as P is J epsilon 0 I say E j for I and J, X, Y, Z or 1, 2, 3, anything you can take. This in the problem it is given in terms of matrix form, so that means you need to express in matrix form. So in matrix form you can write it as Px, Py, Pz. This is epsilon 0, Ix, Ixy. So this is already being discussed in the class. Yx, Yy, Yz, Zx, Zy, and Zz. And we have the electric field Ex, Ey, Ez. So this is the general expression for the polarization in matrix form. So let us see the first case. So when we are applying the electric field, so for the first part, so this part, we need to find out this matrix. So question is asking about this matrix. So let us see one by one. So P1, it is given epsilon 0, 3, 1, 0. This is the response when we have electric field. E1 is 1, 0, 0. So you can just put it in the this general expression. So this P1 is three component Px, Py, Pz, which is 3 epsilon, 1 epsilon, and 0. So that means this form, this we can write it as the matrix for chi. I'm writing as this. Okay, so let us write it explicitly. So chi xx, chi xy, chi xz, yx, yy, yz, zx, zy, zz. And E1 is 1, 0, 0. So if you take the matrix multiplication, we will get the right hand side. What you will get? So only this part of this matrix will remain. Other part will be 0. So when we multiply this by this, chi by 100 will get chi xx, chi yx. So this will pick out the first column of the susceptibility. So that means we know the first column vector of the susceptibility matrix, which is P10. Okay, so this is for P1. For P2, let us see what is the response and what is the electric field. P2 is 142, this is 010. So that means this will now pick out the second column vector of the susceptibility matrix. So this is 142 and A2 is 10. So you just need to put it in the general expression. IXS, IXY, XZ, YX, YY, YZ, ZX, ZY, ZZ. 10. Sorry, this is 010. So this will now pick out the second column vector, which is chi xy, chi yy, chi z. Okay, so that means now if the third vector is like this 001, this will pick out the third column vector. P3 is epsilon 0, 0 to 5, which is epsilon 0 chi matrix. And this is 001. So this will now pick out the third column vector, which is chi xz, chi yz, chi z. So now we know all the elements of the susceptibility matrix. Okay. So third column vector is here, second is here, and first is this one. So you can just write the complete chi matrices. A10, 142, 025. So this is the answer. So is this clear? Okay, if this is clear, then we'll move to the second question. So in the second question, it's given an electric field, which is expression Et as E0 cos omega t minus kz. So it is given electric field of this form is incident on a nonlinear medium with chi m equal to 0 for m greater than 3. So that means the chi m, it is non-zero only for when m is 1 and when m is 2, and other part it is 0. Not so chi 3 is also there because for m greater than 3 it is non-zero. It is 0 for m greater than 3. And the polarization of the nonlinear medium can be expressed as PL summation of PL plus PNL. So this we have already seen in the lecture. So PL expression is epsilon chi 1 E, and PNL it's a powers of E. Okay, so you can express PNL as for this question it's given summation of PNL at different values of omega cos omega it minus ki z. And it is also given omega is nothing but I times omega, and ki is nothing but I times k for I starting from 1, 2, 3. Okay. So the question asks, what is calculate the nonlinear polarization component at the third harmonic frequency. So what will be the nonlinear polarization component for PNL3 third harmonic frequency? So as discussed in the lecture, we'll uh, we'll see what is the dominating effect, how we can express the powers of cos in terms of linear combination of different values of uh, different components of omega. So for now we have given it is chi 2, chi is non-zero up to m equal to 3. So that means P and L is epsilon chi 2 e square is epsilon chi 3 a3. So for third harmonic generation, we need only this term. We need to find out this one. So what we have, we need to first find out EQ first, which is nothing but third power of ET. ET is already given, E0, Q cos Q omega t minus Kz. And cos Qx, if we recall, this we can write it as 3 cos x plus cos 3x by 4. This is the trigonometric relation. So we can directly use this EQ by 4, 3 cos omega t minus Kz plus cos plus cos 3x, which is 3 omega t minus 3 Kz. So that means we have EQS E0 Q by 4 P cos. So I'm just writing it again here as cos 3 omega t minus 3 kz. This is the third harmonic term. Okay. So P and L for the, so if you find out what is epsilon naught chi q EQ, should be epsilon IQ E0 whole 3 cos omega t minus kz plus cos 3 omega t minus 3 kz. So we need to find out what is PNL 3 omega. And what is given to us is the general expression of the PNL. So PNL, it is given summation of omega I, PNL omega I cos omega I t minus KIZ. So this you can, because so I is 1, 2, 3, right? So that means you can write this is for omega. This is PNL omega cos omega t minus kz. So when PNL is 2 omega, 2 omega cos 2 omega t minus 2 kz plus PNL 3 omega cos 3 omega t minus 3 kz. So if you compare this expression with this term, so if you compare 1 and 2, we want to find it PNL 3 omega. So that means this is the coefficient of cos 3 omega t minus 3 kz, which we have already calculated it here. So coefficient of this term is nothing but this, right? So we have PNL 3 omega. It is epsilon IQ E03 by 4. Similarly, if the question asks what is the second harmonic generation, then we need to compare this with the expression that we can explicitly calculate. So from that you can calculate PNL 2 omega or PNL omega. Okay. So is this clear? Or do you need to go through any of this step? Okay. So if it is clear, then we'll move to question number 2, which is a bit complicated one. Okay, so this was question number 1, I think. Question number 2. So in question number 3, we have consider a nonlinear optical medium with non-zero values of chi2 and chi3. And chi-m is 0 for m greater than 3. So this situation is similar to what we have seen in question number 2. Now we have a electric field which is incident on the medium, which is the following expression. So this is a linear combination of a field which is two frequency component, omega 1 and omega 2. And so in the first part, the question asks, what is the general expression for nonlinear polarization? In B part, so this is combination of lot of concepts. So don't get worried. So this will include concept from like third harmonic generation, self phase modulation, third and second harmonic generation. All of these are combined in this quotient. Okay. So in B part, we have identified all the frequency components generated by chi2 and chi3 effect. And in C part, we need to find out what is the amplitude of the nonlinear polarization at the sound frequency omega 1 plus omega 2 due to chi2, and at the third harmonic frequency, third harmonic 3 omega due to chi3. And it is also given, consider the expression for PNLS summation of omega I PNL omega I cos. So this is what we have seen earlier also, and this is just for information we are given. Okay. So first we have, let us write, it is the general expression. So general expression is easy. So because chi for m greater than 3, the chi is 0. So that means PNL is epsilon naught chi2 et square plus chi3 et cube. So et, it is given a1 cos omega 1t minus k1z plus e2 cos omega t minus k2z. So this is given. So let us say this is theta 1, this is theta 2. So that we don't have to write it again and again. So E1 is cos theta 1 plus E2 cos theta 2. So to find out the terms, we need to expand epsilon chi2 E2 square and epsilon E2, epsilon chi2, chi3 E3, E2, E3 cube. So let us see first the chi2 term, which involve E square. So this will be Et square. So this one will be easy because this only involve the square term. So this is a plus b whole square. So that means this is u1 square cos square theta 1, e2 square cos square theta 2 plus 4 e1 e2 cos theta 1 cos theta 2. So we need to express this square term in terms of the cos term when we don't have any power. So this you can write it as 1 plus cos 2 theta 1 by 2. This is 1 plus cos 2 theta 2 by 2. And this is cos A cos B. So you can take 2 here. So 2 cos A cos B will be cos A minus B plus cos A plus B. Right? So now we have all the terms. So if you put these terms here, so I'm just writing the final expression. So you will get E1 square plus E2 square by 2. This is the term where omega is 0. Then E1 square by 2 cos 2 omega 1t minus k2 k1z plus a2 square by 2 cos 2 omega 2 minus 2k2z, and we have E1 E2 term, E1 E2 cos A minus B, which will give omega 1 minus omega 2 t plus k1 minus k2 z, and plus cos A plus B. So this will give omega 1 plus omega 2 t plus k1 plus k2 z. So that means if you see here, the epsilon chi2 E2 square. So due to chi2 effect, we'll see that this chi2 will generate a DC term with omega equal to 0. And what we have? We have second harmonic generation 2 omega 1 and 2 omega 2. So we have second harmonic 2 omega 1 plus, 2 omega 2. And we have some frequency which is omega 1 plus omega 2, and difference frequency which is omega 1 minus omega 2. So we have some frequency and difference frequency. So for this kind of field, for the field when we have two frequency component, omega and omega 1 and omega 2, the because of the chi2 effect, we'll see a DC term, second harmonics, and some frequency and difference frequency. Okay, so this is for chi2. So let us see what is the term that would be for chi3. So for E3 term, which is ATQ E1 cos theta 1 plus E2 cos theta 2 whole cube. So A plus B whole cube, you already know the formula. This is AQ plus BQ plus 3A square B there will be 2 here plus 3AB square. Square theta. The expression for cos q we already know. This will be 3 cos theta 1 plus cos 3 theta by 4. This will be 3 cos theta 2 plus cos 3 theta 2 by 4. And in cos square terms, you can put 1 plus cos 2 theta 1, and here you can put 1 plus cos 2 theta 2. And again, you will be for this kind of term, you will see you have a term cos A cos B. So you further need to expand it, like 2 cos A cos B is cos A plus B, cos A minus B plus cos A plus B. Okay. So let me just write down what will be the answer you will get. Okay, so this is already sorted out. Only we need to see what will be the terms for this. So let us see this first, which have 1 plus cos 2 theta 1 cos theta 2. So this is cos theta 2 plus half 2 cos 2 theta 1 cos theta 2. So this is cos A cos B. So we have cos theta 2 plus half cos A minus B, which is 2 theta 1 minus theta 2 plus cos A plus B, 2 theta 1 plus theta 2. Similarly, for this part, we will have 1 plus cos 2 theta 2 cos theta 1. So you will get cos theta 1 plus half cos 2 theta 2 minus theta 1 plus cos 2 theta 2 plus theta 1. So you have all the expansion. Now you just need, so the final expression will be EQ, which is E1Q by 4, 3 cos theta 1 plus cos 3 theta 1 plus E2Q by 4, 3 cos theta 2 cos 3 theta 2, and we have the term 3 E1 square E2 by 2 cos theta 2 plus half plus cos 2 theta 1 plus theta 2, and the last term is 3 E1 E2 square by 4, sorry, by 2 cos theta 1 plus half cos 2 theta 2 minus theta 1 plus cos 2 theta 2 plus theta 1. So now we have all the terms. Let us see what are the frequency that is getting generated. So we have theta 1. So theta I, this is omega it minus kiz. Okay. This we have taken before. So theta 1 is there. So that means omega 1 and omega 2 will be there. So omega 2 will be there. This is also known as self phase modulation. We'll see in the next session in details. So this is omega 1 and omega 2. So if it is generating the same frequency, we say this is self phase modulation. Now the terms we have is 3 theta 1 and 3 theta 2. So which is third harmonics. So we have 3 omega 1 and 3 omega 2. This is third harmonics. And other terms that we have is 2 theta 1 minus theta 2, 2 theta 1 plus theta 2, which is 2 omega 1 minus omega 2, or 2 omega 1 plus omega 2. There is 2 theta 2 minus theta 1, which is 2 omega 2 minus omega 1, and 2 omega 2 plus omega 1. So this is mixing terms. We'll see this is also known as the four-wave mixing. Okay. So these are the four-wave mixing. So that means for this question, so do you have any doubt up to now? So we have solved this and this. Now we'll see what is the C part. For the C part, we need to find out what is the amplitude of the nonlinear at the sum frequency omega 1 plus omega 2 due to chi 2 and third harmonics 3 omega 1 due to chi 3. I think the steps are easy to follow. Okay, so let us see the amplitude of some frequency, which is omega 1 plus omega 2 due to chi 2. So amplitude is nothing but finding out what is the PNL omega 1 plus omega 2. Some frequency means omega 1 plus omega 2. So for this, it is already given. The expression for PNL is already given. It is summation over omega I, PNL, omega I, cos omega it minus kiz. So that means when omega is omega 1 plus omega 2, which is some frequency, you can write PNL as PNL omega 1 plus omega 2 cos omega 1 plus omega 2 t minus k1 plus k2 z. So the amplitude is here. So we need to find out what is the coefficient of cos omega 1 plus omega 2 t minus k1 plus k2 z in chi 2 term. So chi 2 we have already calculated it, right? Here. So E square is calculated. So if you multiply with epsilon chi 2, we'll get what is the polarization. So all the terms will be multiplied by this. So let us see. Okay. So this term has some frequency component. Cos omega 1 plus omega t plus k1 plus k2 z. Right? So for this one, what is the coefficient? Coefficient is A1, A2. And we need to multiply with epsilon chi 2 so that we can get the value of polarization. So that means okay, 1 minute. Um, okay, so this is E1, E2, E1, E2, epsilon chi 2. For the second part, third harmonics component due to chi 3. So we need to see what is the coefficient of 3 omega. Hmm, where is 3 omega? Okay, chi 3. So here we have 3 omega 1. So this is related to 3 theta 1, right? So this, the component is E1Q by 4. So if you multiply with epsilon chi 3, so this will be the component. So that means we have now for PNL 3 omega 1. We have epsilon naught pi cube E1 cube by 4. So if you ask about what is 3 omega 2, you can see this will be, instead of E1 cube, we will have E2 cube there. So if you know the total expansion, then you can calculate what is the individual component for some frequency, third harmonics, second harmonics, or self-phase modulation. So first we need to calculate what is the expression first, then you can proceed further. Okay. So this question is clear. So do you have any doubts in any of the parts? So let me put it here. If not, let us move to question number 4. Please go through the question once. Okay, so let us see. We have in the question, an electromagnetic wave propagates in a material where the complex refractive index is given by this expression. N is 1 plus ik by 2 and 0. And it is also given the value of kappa is or k is much less than 1. And n0 value we can take it also as 1. Okay. And the incident electric field, it is also given. EZT is E0 e to power I kz minus omega t escape. K is the complex wave number. And the question asks about what is the polarization induced in the linear medium due to the incident electric field. So we have the electric field EZT, which is E0 e to power I kz minus omega t. So for polarization in a linear medium, we need epsilon naught. So this is a constant. We need chi1 because electric field is already given. So how we can calculate chi1 here now? You can see the refractive index is given. So n is given as 1 plus I k by 2. So, and if you recall, this refractive index, you can write it as n is nothing but c by v, right? Which is, if you recall, this is mu epsilon by mu naught epsilon naught. So that means if it is a non-magnetic medium, you can write it n as square root of epsilon r. And this epsilon r is nothing but 1 plus chi1 for a linear medium. So this is the relation between the refractive index and the susceptibility. So we know the refractive index, that means we can easily calculate what is chi1 here. Okay. So n we know. it is square root 1 plus chi1 1 plus ik by 2. So if you take the squares both side, this will be 1 plus chi1. This will be 1 minus k square by 4 plus ik. In the question also it's given k is much less than 1. So that means we can neglect this term because it's a square of a non-negligible term. So chi1 now we have find out it is I up. So that means we have the polarization P as epsilon naught chi1 E, which is epsilon ik E0 e to power I kz minus omega t. In I you can write it as e to power I pi by 2, right? So that means we have the term epsilon k E0 e to power I kz minus omega t plus pi by 2. So here we can see also there is a phase difference between the polarization and the electric field that we have earlier. Okay, so this one is more conceptual one because if you know epsilon, what is the relation between refractive index and the susceptibility, then you can easily find out what is the total expression. So is there any doubt? Otherwise, we'll move to question number 5. So this may be, it will be the last problem for this live session. Okay, if there is no doubt, let us see what we have in question number 5. So it is given the susceptibility of a linear medium is expressed as, so chi1, the matrix form of chi1 it is given, it is 2 0 0 0 1 0 0 0 1. And the incident electric field is also given, which is E0 xk plus yk. And the question is asking about what is the angle between D and E. D is nothing but the electric displacement vector and E is the incident electric field. So for this, what we need to find out first, we need to find out what is D now because E is already given. And it's a linear medium, that means we can write D is epsilon naught E plus P. So for linear medium, we have P is epsilon chi1 E, which is epsilon naught identity matrix plus chi1 E. So this is for E. And what is I here? It is the identity matrix. I think all of you know what is it. So that means D will be epsilon naught 1 plus chi1 will give 3 0 0 0 2 0 0 0 2. Dot E is already given. It is E0. So let me take out here 1 1 0. So this will give E0 epsilon 0 3, 2, 0. So we have the matrix representation for D. Now we can easily find out what is the angle between them, because angle is nothing but cos inverse D dot E by mod E. So can you please calculate it and let me know the answer? D is already you calculated, this is this, and E is E0 1 1 0. So what will be this? What will be the angle? So I'm just writing out the answer. I think you can easily calculate it. This will come around cos inverse pi by root over of 26, which is around 11 degree. Let me know whether you are getting the answer or not. Okay, so let me solve the last question also, because this is the last will be. So it is given the susceptibility near an atomic resonance. It is given by this expression. So where omega 0 is the resonant frequency and gamma is the damping coefficient. And the question says at omega equal to omega 0, what will be the dominant contribution to P? And there are four options. Option A says P will be in phase with electric field, and B says it will be pi by 2 out of phase with E. Option C says it will be pi out of phase with E, and option D says it is independent of E. So I'm just giving this to you to solve it. So answer will be this one, option B. Okay, so let me know whether you are getting the answer or not. We'll see if you are getting stuck anywhere. I will clarify the doubts in the next live session. Okay, so this is all for today's live session. Let me know whether you have any doubt in any of this problem. I will try to clarify that. Otherwise, we'll end the live section for today. So, Lina, do you have any doubt? Okay. Okay, then. So thank you for joining the live session. I hope whatever I've solved, it will be useful for you. So we'll meet on next Monday, same time from 6 to 8. Okay. And we'll try to see some more problems related to the contents that is related to week 11. Okay. So thank you for joining the session. Bye everyone.